So welcome back. This video is going to introduce finite mixture models and Gaussian mixture models in particular. The way I'd like to start out is with an example to motivate why we need this. So I have a kind of famous data set called the Old Faithful data. Old Faithful is a geyser at Yellowstone National Park. This data set has been analyzed in a lot of different statistical textbooks in the past. The data records the length in minutes of different eruptions. We have roughly 100 cases. Here's a density estimate, which is like a histogram of the raw data. And so what we see are two modes. We have a large mode off to the right. The center of this mode is about 4 minutes. Then we have another mode that's around 2 minutes. You're more likely to see a longer eruption than you are a shorter eruption, but there are very few eruptions in between. So it's very unlikely that you'll see something that's a bit under 3 minutes. In my previous video, we talked about the biases of the k-means method. And a quick inspection of this plot suggests that k-means is going to have some, let's just say, minor difficulties with this. I'm not sure they rise to the level of being major difficulties. One of the biases of k-means is that it's biased towards having equal size clusters. Well, in this case, we've got two unequal size clusters. So what I would expect to happen with k-means is that it should let the mean of the smaller cluster drift to the right to start to include some of these sparse observations. What could happen then with the mode of the larger distribution is that it also will drift right. The larger distribution can leave the left tail to the smaller cluster and spend its energy modeling the right tail. The other thing that we know about k-means is that it does hard assignment. So there will be some dividing point where all observations to the right of that get assigned to the right cluster, and all observations to the left will get assigned to the left cluster. As a consequence, we're going to have the tails of these two distributions truncated. So without the left tail of the larger right mode, we would expect the mean to drift a little bit to the right. With the smaller distribution, we would expect the mean to drift a little bit to the left. So I would expect that k-means will overestimate the mean of the larger one. We've got at least two biases working against each other with the smaller mode. So the equal cluster one will push the mode to the right. The truncated tail, the truncated right tail, will push the mean to the left. And so I don't quite really know what's going to happen to the smaller one. So let's go look. So I ran k-means. I also ran a Gaussian mixture. So that's what we're going to be studying this week. And so Gaussian mixtures produces two means, as does k-means. And we can see that the larger cluster, so the larger cluster in this case has 74 cases, with k-means as a mean of 4.08. With Gaussian mixtures, the mean is 4.02 if you round to 2 decimal places. So it looks like k-means has a small bias as we anticipated. I'm not sure how upset I should be about a bias of that size, but it exists. So with the smaller mode, k-means estimates the center at 2, while Gaussian mixtures at 1.89. So it looks like the equal cluster bias wins out, and the mean of this smaller cluster drifts over to the right. When it comes to the relative sizes, it looks like the smaller cluster is about 30% of the cases with k-means. With Gaussian mixtures, it's about 26%. So we see the bias towards equal size clusters manifesting itself with k-means. There's also issues with these within cluster standard deviations. K-means estimates the larger within cluster standard deviation to be 0.42, whereas the Gaussian mixture is about 0.50. That's probably due to the fact that we have hard assignment, and k-means doesn't account for the long left tail of the right mode. When it comes to the left mode, we see k-means estimating it to be 0.35. The Gaussian mixture estimate is about 0.18, so this one's about half the size. What's probably happening here is by allowing the mean to drift to the right, k-means swallows up a lot of these observations in the middle, which inflates the standard deviation. I've also run this in Python. Python actually comes up with slightly different answers than the R Gaussian mixture library, but the two are much more similar than the k-means output. So I hope that gives you some motivation for why the finite mixture model and Gaussian mixtures in particular are going to be of use to us. So what is a finite mixture model? As with k-means, we're going to start out with n observations with p measurements. Xij will be the measurement on subject I of variable j. We're going to assume that there's big K unobserved classes exactly as we had with k-means. But now we're going to assume that there's a random variable y which indicates the unobserved class. So y is going to be a discrete random variable taking values 1 through big K. So finite mixture models concern themselves with 3 or maybe 4 distributions, depending on which ones you want to count. The first distribution is called the prior distribution. The prior distribution gives what I like to call the unconditional probability of group membership. So if you draw an observation at random from the population, what's the probability that it comes from any one of the classes? I'm going to use the Greek letter eta to denote these prior probabilities. And note that the prior probabilities must sum to 1. So these etas specify a probability distribution and therefore must sum to 1. An implication of this is that we only have to estimate big K minus 1 priors, because if we know big K minus 1 of them, the last one we can find by subtracting from 1. The second type of distribution is called the class-conditional distribution. I'm going to denote this by f sub k at x. What the class-conditional distribution tells me is if I know that you are from class little k, f sub k at x tells me the PDF. The picture to keep in mind is as follows. Let me illustrate these distributions with a simple example. Let's take p equal to 1. We're going to take big K equal to 2. So I've got one manifest variable and there are 2 unobserved classes. The class conditional distributions tell me what is the distribution of an x if I tell you which class you're part of. So for the purpose of this example, suppose I have the blue distribution. So this blue distribution is going to be the first class conditional distribution. So I'll call it f1 at x. This is going to have mean, mu sub 1, and standard deviation sigma sub 1. I'll use red to indicate the other class conditional distribution. I'm going to try to make this one have larger standard deviation. So kind of following what I had with Old Faithful. Both of these are PDFs, so the area under both the red curve and the blue curve had better equal 1. So the mean of this is mu 2. The standard deviation of this is going to be sigma 2. I've rigged this so sigma 2 is bigger than sigma 1. And let's just label this. This is f2 at x. There's also a prior distribution. Let's say that the probability that y is equal to 1 is, say, a fourth. Something like what we had with Old Faithful. The symbol for this is going to be eta 1. Then the probability that y is equal to 2 would be 3/4. We're going to denote that by eta 2. So the way we generate data is we first draw an observation from this prior, then a quarter of the time we're pulling observations from this distribution with a smaller standard deviation. 3/4 of the time we pull it from this distribution. So this gives rise to what I like to call the observed distribution. So we'd end up with a smaller mode and then a much larger mode. So this is our observed distribution. So if we go back to Old Faithful, this was the observed distribution. This is the data that I've observed. Where did this come from? Well, I'm going to assume that there's a mixture of two Gaussian distributions, and I'm going to allow for one of these Gaussians to be more common than the other. These class-conditional distributions are multivariate distributions. So X is a p-dimensional vector. An issue that comes up whenever you have a p-dimensional vector is that there can be a lot of covariances that you have to worry about. So if I have a p-dimensional vector, what is the variance of X? So X is a vector here. This is going to be a p by p. So this is going to be a p by p quantity. And so notice I have p times 1 plus p over 2 entries. So the number of variance terms that you have to estimate is going to grow very quickly with p. So one thing that we often do is something kind of similar to what you do with naive Bayes. And that is you assume class-conditional independence. What that means is all of these off-diagonal variances are assumed to be 0. So independence implies that your covariances will be 0. And then you only have p variance parameters to estimate. So we often do this. We don't always do it. The next 2 videos will talk a lot more about this. The last distribution that we worry about is called the posterior distribution. The posterior distribution says, what is the probability of some y given the additional information x? Using Bayes' theorem, we can compute these posterior probabilities from our class-conditional and prior distributions. So let's take an example. Suppose that I had an x out here. Let's just call this x1. So if I give you some additional information that an observation, so maybe x1 is sitting out here someplace. So if I gave you some additional information that my x is here, the posterior probability, so probability of y equals 2 given x1 would be close to 1. So there would be almost no probability that I would draw an x1 if my true distribution were the blue one. Whereas the probability of observing such an x1 would be pretty high if I had the red distribution. Likewise, an x2 out here would be highly likely to come from the blue distribution, fairly unlikely to come from the red distribution. An observation somewhere in the middle would have pretty high probability coming from either. So the beauty of these finite mixture and Gaussian mixture models is that we can reflect the uncertainty of which distribution these observations come from. I'm now going to generate some data that's kind of like the Old Faithful data, except that now I'm going to know the answer. In this example, we'll have big K equal to 2 classes, P equal to 1 manifest variable, and I'm going to label my classes 0 and 1. Since the 2 prior probabilities have to sum to 1, I'm going to have a single eta that indicates the probability that you come from class 1. 1 minus eta then is going to be the probability that you come from class 0. So in the 2-class situation, this notation's a little bit easier. I'm going to assume that my class conditional distributions are normal with different means and different variances. So the class conditional distribution is just the formula for a normal distribution with mean mu sub k and variance sigma k squared. The unconditional distribution will be the sum of these two class conditional distributions weighted by the priors. Our job is to estimate the parameters. So in this case, the parameters are the two means, the two variances, and the prior probability eta. We're going to do that with maximum likelihood. So if I assume a sample of n observations, multiply all these unconditional PDFs, take the log, we end up with the following expression. So this is actually a difficult expression to maximize. One trick that's often followed is this. If we knew the values of y, so if we knew which class each observation came from, then the likelihood would be very easy. We're just estimating means and variances, and that's a problem that any introductory statistics student has addressed. So we're going to do something very similar to the k-means algorithm, where I first estimate which class you're from, or at least the probability of which class you're from. Then with that fixed, I estimate the means and the variances, and I update my priors, and I iterate between these two steps until convergence. So I implemented a simple R function to try this EM algorithm out, and I generated data using the model I specified before. So my class conditional distributions are normal with a mean of 0 and a standard deviation of a half. That's this distribution. If you're in class 1, you have a mean of 3. So the mean of this distribution is 3. The standard deviation is 1. And I'm going to say for this example that 2/3 of the observations are going to come from the top class, 1/3 from the bottom class. So combining the two class conditional distributions and the prior distribution, we end up with the following unconditional distribution. When you run my software on it, you end up with pretty good estimates. So the means are 0.19 and 3.03. The standard deviations are 0.6 and 0.95. So the correct answer was 0.5 and 1. Well, we're pretty close. The prior was estimated to be 0.65. Well, the correct answer was 0.6666 something. Well, let's go see how we would solve this problem using the MCLUS software. So the first thing to note is that instead of using big K, MCLUS refers to the number of clusters as big G. I simply pass my X matrix, I can tell it how many clusters I want, and it finds it. The answer gets stored in a list that has sublists in it. So fit$parameter has the parameter estimates, pro stands for proportion, and we see a vector giving the prior probabilities. So 0.65 and 0.35 are the probabilities that you're from the first and second class. Fit parameter mean gives the mean values. They found exactly the same values that I did. Fit parameter variance sigma squared gives the variances rather than the standard deviations, and those also match what I got. If we use k-means, we see the same biases we saw with the Old Faithful data. I'd now like to point out something that's kind of counterintuitive about the posterior distribution. So let's work out the posterior distribution for class 1 given some x. Well, the definition of posterior with Bayes' theorem is take the class conditional distribution times the prior. Think of this as the unconditional distribution in the denominator. So I dropped in my prior. So the question I'd like to answer is, which values of x should be assigned to group 1 versus the other group? So the answer to this could be assign an observation to group 1 whenever the posterior probability is bigger than 1/2, or you can also think of this as this posterior probability is larger than the posterior probability of belonging to group 0. Either way, we assign to group 1 whenever this ratio, so this is the posterior probability of belonging to group 1 instead of group 0, exceeds 1. So I'm going to go right in the equations. They get kind of messy. What results is e to a quadratic expression. Let's go take logs of both sides. So the log of 0 is 1. And then if I take a log of the right-hand side, I end up with just that quadratic. If we take logs, so I have a quadratic inequality that actually factors. I rigged this so that it would factor nicely. And we end up with 2 roots. So this says, assign to class 1 whenever x is greater than 1. That makes total sense. Or when x is less than -3. That doesn't make much sense. So what's going on here? Well, let's go graph these 2 class-conditional distributions. The right distribution has larger variance than the left distribution. So this one had a standard deviation of 1, whereas the left distribution had a standard deviation of 0.5. What that means is the tail for the blue distribution is going to go to 0 more slowly than the red distribution. So these 2 distributions cross at 1. So any observation greater than 1 we're going to call blue. Any observation that is less than 1 but greater than -3 out here is going to be called red. But these tails cross again at -3. And so we can see that really clearly if we graph the 2 posterior distributions. So that's kind of a quirk of the finite mixture model. You can get some kind of strange decision boundaries. So what I hope you understand at this point are the component distributions of a finite mixture distribution. I hope that you can estimate these in R or Python and interpret the output. In my next video, we're going to start talking about what happens when you have more than one variable, so when p is greater than 1.